Sure. All right, let's get started. So I will apologize in advance because I am dealing with a pretty good cold. As my earlier class can attest to, I was hacking a little bit, not too bad. So watching the video on this might be annoying. I apologize. I've done cough drops and cough medicine and all different kinds of things, and it's had relatively not the greatest impact or effect. But the Tylenol are really effective. So I apologize for making all these weird noises. It's not what you expect, but we'll go from there. Okay, so there was a question before class officially started, which is how do you do the open circuit and short circuit tests? Here's the homework problem. Here's the open circuit test. Let's go ahead and draw a picture. Open circuit test is going to calculate R sub C and JXM, right? Because under no load conditions, there's very little voltage drop from the series elements, so we can neglect it. So over here, we have 7,200 at an angle of 0. My current going in is 0.54 or 45. What's the angle associated with the current? 90? Everybody agree? You don't know it, so it's just call it theta. Call it theta because we don't know it. What were you going to say, Aaron? Call it 0? What's that? Oh, somewhere between 0 and 90. Yes, that's true. Except it's not true. Eli would smack you upside the head. What does Eli say? Ah, there we go. Because the current lags the voltage in an inductor circuit. So how could it be between 0 and positive 90 if it's lagging? What's that? Oh, fair enough. Okay. Even though there's no leading and lagging of magnitude, whatever. All right. So how do we get theta? Well, remember theta, the definition of theta is it's the angle of R. And if you remember, S equals VI conjugate is going to give us VI magnitudes, and the angle is theta V minus theta I. Is there any other angle that has theta V minus theta I in it? How about Z? Right? This is the same angle, isn't it? So we need to get that angle from the power triangle. So here's P, here's S, which is just V times I, magnitude only because we don't know what it is. And then we can calculate theta. Right? Can you calculate theta here? All my Oscar friends? You do. It's in the test data. Can you get P? You don't need to get it. It's given. Can you get V times I, which is S? Yeah. Sure. So you can get theta, which means you can get theta for the current. And remember, it's lagging, as Aaron was talking about earlier. So we put the negative theta there. And when we do the open circuit test, Y open circuit is I at an angle of minus theta divided by V at an angle of 0, which is equal to 1 over R sub C plus 1 over J XM. Can you get that? Is that enough of a hint to do that problem or part of the problem? Inverse cosine, right? Because Oscar had a heap of apples. It's the inverse cosine of the opposite over, I'm sorry, the adjacent over the hypotenuse. So if you do your trig identities, the cosine of theta is equal to P over S. It's a right triangle, so you can use your trig identities. No, they're the opposite angle.
Yeah.
So they have the same magnitude angle, if you want to use that term that Noah used before, but it's just as a negative number. And why is that? Because right here, right? These two, aren't they the same? Theta V minus theta I, theta V minus theta I. So they will have the same angle. Noah, are you wagging your pen at me for a reason, or are you just okay?
Okay, so then for number 2.
But wait a minute. Are you done?
No. I got it.
That's okay. Would you rather just finish this one? So how do you do the short circuit test? It's exactly the same, but now I have R equivalent and JX equivalent. I have 250 at an angle of 0. And I have a current of 13.8, we'll just call it 9, at an angle of minus theta. Do your power triangle, solve for theta, and Z, we'll call it short circuit, is equal to V divided by I, which is equal to R equivalent plus JX equivalent. Yes, sir.
So that I has an angle associated with it, right?
In every case, when we're talking AC, voltage and current must have a magnitude and an angle.
So in that case, the angle of V would be, you take out 0, and the angle of I, how would you put that back to the if it's a positive angle on the bottom, it would be a negative angle. That makes sense.
The negative angle, all I'm saying is the negative angle from right here, that's the current, right? I have to put it as a negative angle for a couple of reasons, but they're sort of linked. The first reason is we know it's Eli, right? The current must lag the voltage. And we didn't, assume anything. We know that it's 0. We're picking our voltage as a reference. So we force that to be 0. And the reason why we force that to be 0 is because the angle theta V minus theta I is going to be based on 0 if that's going to have an angle associated with I.
It would still be, in this case, it would still be 0 minus the angle of I. Right?
Correct. Yep.
Okay, so it would be, if in this case, I was
I is always a negative angle in an inductive circuit.
yeah, so it would be,
Okay.
yeah.
So the short circuit and the open circuit are basically the same. You just solve for Z for the short circuit and Y for the open circuit. Helpful, not helpful? Now do you have a clue? What was the difference between before and after? Or right now, I should say. Say that again?
I realize
Directly first.
directly inverse the angle.
Well, you do, and this is just one added thing, so it's a good point, Aaron. Remember, that's S equals VI conjugate. So the angle associated with I is going to be the conjugate of those two. And since this is an angle of 0, it's the conjugate of theta, right? You guess? Do you remember that equation, S equals VI conjugate? Because remember, S is equal to VI theta V minus theta I. It has to be the angular difference between the two. And so that's why we have to use the conjugate term. Complex conjugate. So if I have A plus JB, the complex conjugate of that is equal to A minus JB. You just take the negative of that term. If I have A at an angle of B, the conjugate of that, or as a complex conjugate, you just take the negative of either the angle or of the J term. So we get lazy engineers, right? Another way to say that is efficient. When we say lazy, it really means we're just trying to say less words. When I say conjugate, it really fully say it. It's the complex conjugate. So just take the negative of the complex number. And you've been doing complex numbers, complex conjugates for a while. So don't you have to multiply by the complex conjugate of that in the denominator to get rid of the complex number in the denominator? Do you remember that from algebra 2 or when you had complex numbers? Do they do that in algebra 2? Do they do complex numbers? They did calc 1? Huh. I'm not sure when they cover complex numbers, but it's just an algebra thing, right?
Yeah.
You're just trying to get rid of you just try, when you square the j term, it becomes -1, so it goes away. That's why you do it. But I'm not sure if it's an algebra 2 thing or if it's, I'm not shocked if it's calculus because it is complex numbers, which kind of throws people for a loop, but it's hopefully not too complicated. You get enough to handle number 3 now? Okay. Noah, did you have more questions? Said something about number 2?
Yeah, I think I would probably went right with there, but for number 2, then, for the impedance of the fluid. Or the impedance secondary, sorry, how do you pull the
Which part are you talking about? Well, I'm not looking for the angle. I'm just looking for the magnitude Z.
Oh, okay.
Because the angle can be whatever it needs to be, as long as it's fully loaded at 100 kVA. It could have a power factor of unity or a power factor of 0.
I mean, realistically, you couldn't have transformed without a conductor by nature, but for this,
But we're talking about the load. We're not talking about the transformer itself.
yeah, the transformer without.
So we look for a transformer that without the power factor, and we couldn't come up with that.
No, you just put a magnitude of Z. Yep. Yes, sir.
So question 4, how, I feel like it's the reverse of like the stuff. We can go through that.
We're doing voltage regulation today.
Okay. About that, and I was like.
Yeah, voltage regulation. We'll be talking about that today. But you guys asked such good questions. I haven't been able to get there. So this is great. I love this. This asking questions about the homework means you've been working on it and you're trying to learn. So I appreciate that. So please ask more questions. It makes it, like it's a more interactive thing. And so this is helpful to me, which is what we need to cover and whatnot. So are we good on the homework? This is a good investment. I said it's a great investment, but is it 10 or 15 minutes worth your time, class time? Okay. All right, let's go back to PowerPoint. So voltage regulation. Problem number 4 in the homework. So voltage regulation is another way to say the quality of a supply. And it's a scalar number, so we can't have any angles associated with our J terms. It only has to be magnitudes. And so how do we calculate it? We take V no load. Magnitude, sorry. And we subtract V full load. And we divide it by the full load value. And the reason being is because when you have a transformer, it's fully loaded or nominally loaded, let's say. And then something happens to the load, it trips offline. What we want to do is we want to see what that secondary voltage floats to as the load is instantaneously removed. That's the no load conditions. And the reason why is because here is my source, and this is owned by the utility. And there's a bunch of load there. And they've adjusted that voltage so that the voltage over here is approximately nominal. We've talked about that a couple of times in this class. Remember, you're the customer. You pay the utility for power. If they're not delivering a quality product, you're going to go someplace else. A quality product from an electrical perspective is voltage is within ratings, and the current is within ratings. If neither of those exist, at some point, you're gonna be sick and tired of burning out your toaster oven and your laptop and whatever that stuff. And you're gonna go to somebody else, or you're gonna complain to regulators, and they're gonna shut all the utilities down. And so they have to have the ability, and they're constantly doing that throughout the course of the day, to make sure that the voltage at the load where the customer demands it is within nominal plus or minus a certain amount of tolerance. So if this trips, if the load opens up for one reason or another, then this voltage over here is going to float pretty high because you were getting a voltage drop across that transformer. Now, if there's no load on the transformer, the voltage drop is going to be zero. So I've got a pretty big voltage there, or potentially pretty big voltage. So that's what we talk about for the no load, that output floats. And then we want that voltage regulation to be pretty reasonable. So let's take a look at an example. We have this really simple configuration here, 100 kVA single phase transformer. I'm so sorry. I know this is annoying. I can't stop it or else I'll. Excuse me. Terribly sorry. I'm not trying to be rude. Needed that. Clear my throat. Okay. So here's our case where we have 200 to 400 volt transformer. It's internal short circuit reactance. This is essentially just that value of R and X combined together. We're not going to worry about R sub C and JXM because they're usually pretty large. They don't really have an impact. And what we want to do is calculate the voltage regulation across that transformer when we go from fully loaded at unity power factor and rated voltage. So it's delivering rated voltage on the secondary side or the 400 volt side. And then we want to see when that voltage disappears, what the load disappears, what happens to the voltage. So the first thing we need to do is what is the actual current through the transformer under full load conditions? It's unity power factor. So we know that the current is in phase with the voltage. So at full load, 100 kVA at an angle of 0 divided by 400 volts at an angle of 0. And this 0 right here is because of unity power factor is going to give me 250 amps. Now we have 400 at an angle of 0. This is wacky. For almost all your circuit analysis up to this point, you always had the source at 400 volts, right? But the customer is more important. So you want the 400 volts to be at that end, and then you're going to adjust your supply voltage to deliver that 400 volts. So 400 is at the reference terminals. And now we've got 250 at an angle of 0 flowing through that reactor. We'll just show it as a reactor because the resistance is small enough we can neglect it. Now, we need to calculate the voltage at the source. So it's just KVL. 400 plus the voltage drop across the reactor gives me 400.8 at an angle of 3.58. When I'm calculating the actual voltage regulation, this angle here is not relevant. So let me move this out of the way. So the voltage regulation, be no load. If the load goes away, this power supply, which has been adjusted, does not instantaneously adjust. So if I go from 250 at an angle of 0 to 0 instantaneously, then the voltage drop goes to 0. So my output here now is going to flash to 400.8 volts, right? It's not going to be at 400, it's going to be at 400.8. So the no load voltage is 400.8. The angle, don't worry super duper about the angle, we don't need it. The full load voltage, we set that as our reference as 400. So we plug it into our calculator and we end up with 0.2% voltage regulation. Okay. How does that apply on the homework? You're going to go ahead and you're going to figure out what the load is. So it's 50 kV divided by 240 at an angle of 0. What is the angle here? It tells you right here, right? Doesn't it tell you the angle? The angle is a 0.8 lagging power factor. So inverse cosine of 0.8. And don't forget to take the conjugate, right? What tells you the angle right there. So how to apply this to problem number 4, this is I full load at a 0.8 lagging power factor. And you know it's lagging because the current will lag the voltage when we plug this through. Okay?
I have a question.
Yes, go ahead.
You said the voltage regulation you just calculated was 0.2%. Is that
Yes.
good or bad? What is
That's
a
really good.
range?
That's
Okay,
really good.
How bad can it get?
So it depends on the application, but going to your house, the rules are they can be no more than plus or minus 5% of nominal. So if your
Okay.
voltage is 240, you can go up to let's say 234 and down to not 234, 250. Yeah, let's say 250.4. Down to 226 nominal.
Thank you.
Yep.
Thank you.
Now, if you're at the utility levels, they'll have different rules. Their voltages have to be able to go up to plus or minus 10%. They could run at a much bigger range. And that's because the customers have a tighter range. So I have to push my generators and my transformers much harder to be able to make the systems work. So generators, transformers, they operate at a much wider range. It doesn't sound like much, but going double is actually quite a bit. All right, so you
Thank
do it
you.
with 0.8, you do it at unity, which we just talked about, which is 0, and then you do it at minus 0.8, because for a leading power factor, we know that our full load is going to have a positive angle of theta. So if you plug that into here, you need to make sure you have a negative sign, right, for the value to make sure that you have a leading current. Okay. Here's another example. Let me move this down over here. 240 to 2400 volt transformer has a goofy impedance, but that's okay. It's got a lot of numbers. We want to determine voltage regulation for full load operation at 0.85 power factor. It's more the same, right? First step we do is find the load current at that power factor, 312.5 at an angle of minus 31.7. Notice this was put in as a positive number because of the fact that it is a lagging power factor. Now we find the voltage at the secondary of the transformer. So 240 plus the voltage drop gives me 252. And then we just go ahead and plug that number in. When no load occurs, the power supply has been adjusted to deliver 240 volts at a 0.8 power factor, 75 kVA. Now that load drops out and the voltage that we see at the secondary side is the 252 that we see here. So 252.49 minus 240 divided by 240, you have a possibility here that you can exceed PUC recommendations for the customer. So what would you do? If the PUC is going to smack you around, what I would probably do is get a 100 kVA transformer. Because if the load is at 75 kVA and this impedance is, kind of the same, maybe a little bit smaller, 100 kVA is going to end up having a smaller impedance. So you're going to get a less voltage drop. Yes, sir.
When utility makes changes to the way the spread operates, do they have to include this information in the PPCM file?
A what file? CB?
EET321, like the class file.
I don't know what CPCN is. I've never heard that term. They do, so the information that the utilities contain, so it's different, but they will have all the information down to the transformer outside your house. And usually we'll have the metering information as well, because they want to make sure they get paid, right? They want to know the meter number associated with the home so they can send the bill to the correct customer. So they do have that information, but they don't have that all in one aggregated place, because your model of your system down at the distribution level is it's got a lot of details. Like, sounds crazy, but a pole outside your house is actually an engineered piece of equipment. And if you want it to be precise, you actually have the pole height, the hardware at the top of the pole, not only including the transformers, but nuts and bolts and cross arm wood pieces and all these different supports, because when they have to repair it, they're going to go out and they're going to send an exact replacement. And so they got a bucket truck, and they want to make sure that the bucket truck has all the equipment. They don't have a moving warehouse with all this stuff. So they send somebody out with all the equipment so that it's easy enough for them to repair. Go ahead.
But I did look it up, I think it's the end of the certificate of public convenience and necessity. It's a permit that a utility has to get to provide service to a new geographic area, enter into a new franchise agreement, or construct and operate a new facility or an extension of the facility that is outside the ordinary course of business.
Okay.
Anytime you modify a substation, or anything, you have to do it.
Yeah, I've never experienced those. I'm not on the business side of things, so I've never done that. Sounds like more of a business form than anything than a technical or engineering thing, so.
I had to do engineering work in the court.
Okay,
Filings.
yeah. Maybe they had some technical justification or something like that, or something like that. That could be possible.
Prove that like you're below 150 million of property.
Yeah. Sounds like,
You don't know.
I don't know. No, I'm not familiar with that. So I've never filled one of those forms out. So not in my area of expertise. Do that in MATLAB. I like MATLAB. So here's how you do this in MATLAB. This is a MATLAB published file, which not only has the script that I wrote for this, but then it has all the information. And if you're really suave, you might be looking at this and say, I wonder if this would be helpful on the homework. Hint, hint, wink, 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 for what it's worth. Any questions on the MATLAB file? You don't have to do this. Just offering it up there as trying to be helpful. You also have, you don't have to take pictures of these, because these slides are all available to you, right? In the course folder, in the content for this day. So you're welcome to take pictures. It doesn't bother me, but if you don't want to, you can also see that all these are available to you. And I'm pretty sure you can copy from PDF directly into MATLAB. I believe so. As long as you have the PDF writer, I think you can copy text over. And I think, don't college students get free access to Adobe PDF? Oh, they don't anymore?
Anybody can download Acrobat Reader. for free, but-
This is the writer. I think you to edit text, the writer.
Nothing.
Okay. Well, I know there are free versions that can access writing stuff. And so, if you need to, it's not much to type either. So what it's worth. All right, let's go ahead and connect some transformers. And why do we need to connect transformers? Because there's no such thing as a three-phase transformer. Say, what? Well, we call it three-phase transformer, but it really is single-phase transformers connected in such a manner to provide a three-phase load and source. So what we need to do is we connect those three single-phase transformers, and we're going to connect them in either delta Y configuration to go ahead and do that. Now, most of the time when you buy a transformer, it's a three-phase transformer all packaged up in one piece of equipment. They might even share a core, but the reality of it is internally, it's actually interconnected so that you have three individual windings around a core or a bunch of different cores, and then they provide the three-phase output. So let's take a look at our three individual transformers. You can see that they're labeled. Each one is 100 kVA at 5%. They're all exactly the same. Now, I'm gonna go ahead and I'm gonna connect this in a Y configuration, which means on the primary or power side, and you can tell this is the primary side because this is where our sources are provided. I can take the sources and I can have that a delta or Y, it doesn't really matter to me, but I'm gonna connect the transformers so that they are Y connected on the primary side. So I'm gonna take all the neutrals and run those to the exact same point. Well, they're all interconnected. And then the incoming power comes from these three lines. So this is a Y connected, and you can draw it if you want. Transformer on that side. The secondary side of the transformer, remember, it's a completely electrically isolated from the primary side. So you can connect it in any way you want, Y or delta, doesn't matter. I want this to be Y, so I'm going to connect the three neutrals together as shown, and then I'm going to run out phase C, phase A, and phase B, and I'm going to run those to my loads. I have a delta connected load here and a Y connected load here. And the transformer has no issue with configuring it this way. None whatsoever. Matter of fact, you can tell the transformer manufacturer you want it to be Y or delta, and they're perfectly fine to connect it any way you want. It does have a little bit of an impact because you see over here, I've got 240 volts here and 120 over here, but my line voltage on my secondary is 208. So the insulation across this winding over here only has to be rated for 120. But if I was connecting this in a delta and I wanted it to be 208, then this would have to be 208 volts, not 120 volt, right? So this is a pretty common connection if you want three phase going to a residential facility, not a residential, probably an industrial facility. And by the way, where do you typically see three phase loads? Obviously here on campus, because we're a pretty big load. Some bigger manufacturing facilities, like if you went to the airport, there's a GE place that they make turbines there. They would have three phase loads. How about some less obvious ones? We know your house is single phase, right? How about a Walmart? That's single phase or three phase? Most likely going to be three phase. And the only reason why it's most likely three phase is because it's a big load. I mean, you got 100,000 square feet with refrigeration and air conditioning and all that stuff. It just is a really big load. And the utility is going to be sorry, we can't give you 5 MVA on a single phase line. It would just destroy our system. So Walmart almost guaranteed will be three phase. How about let's step down a little bit. What's your favorite restaurant? Sit down restaurant. Taqueria, is that a sit-down restaurant? Pat's, okay. How about Pat's? Is Pat single phase or three phase?
Larger.
Cooking, well, let's assume that it's a gas. No, it's a pizza place, right? So it's gas, so they don't need a lot of power for that. What would be the power demands? Heating and ventilation, you can get single phase, right? Everybody's house here, you have heating and ventilation. That can be single phase pretty easily, unless it's a huge facility. You're missing one very, very, very important piece that has a tremendous load, surprisingly. Yeah, the dishwasher. Why is the dishwasher such a high load? Temperature? You got to run that water to 160 plus degrees, right? Anybody know about sanitation requirements?
Yeah.
It's like 160 degrees for 2 minutes or something crazy like that. And then it sanitizes the plate. So that's when you take the plates out, they're burning hot because if they're at 160 degree water, but they have to be that hot for 2 minutes so that you kill all the germs and bugs. But I said something otherwise very important. Anybody here have a dishwasher at their apartment or house? When you hit start, how long does it take to wash the dishes? 2 hours? Would you be okay if you were the owner of Pat's and you put the dishwasher on and 2 hours later you got clean pots and pans and dishes and all that stuff? You need 2 minutes. So what ends up happening is the water's not coming in there at 160 degrees. Everybody would scald their hands. So it's coming in at 120. And what they do is they have these massive heating elements, massive, 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 that heats the water up very, very quickly to 160 degrees. And they have really strong pumps and motors to drive really high pressure so that when you take a plate out that's been sitting, in whatever sauces and cheeses and all that stuff, and that stuff gets pretty sticky, it's got to come clean every time. So dishwashers are probably the biggest problems at restaurants because you need some dishwashers 1 minute. If you get the temperature high enough, right? If you put the water temperature like just below boiling, 210 degrees, germs will die really, really quickly. So it's part of the pasteurization process. When they pasteurize milk, they do the same thing. But that's a big thing. Also, Pat's is not a great example because Pat's is kind of an older establishment. How about we go to, I don't know, Texas Longhorn for those fans? You're in a restaurant, you're enjoying a fine meal. All of a sudden it smells like garlic or onions or whatever because they're cooking something in the back. Is that really going to make your experience pleasant? Probably not. So over the cooking area, they have big ranges that take out hoods that take out a lot of smell, and they have pretty powerful fans to do that. So most restaurants, decent sized restaurants, sit down, will tend to have 3-phase power, and it's because of the dishwashers. How about the next level down? How about a Gap store? Another way to call those generic term is called a dry goods store. Anybody know what the term dry goods mean? What's that? Don't eat it. Usually means no moisture, no water. So you could have a dry goods store with pasta, right? Many dry goods stores don't have 3-phase because you just have heating and ventilation. In lights, you don't need much power demand there. So unless you're like the size of a Kohl's, which is, massive, you're most likely not going to need 3-phase power. Yes, sir. Movie theater? Anybody have any ideas? Probably size dependent. Again, the heating and ventilation systems, they have a certain requirements about how much airflow they need to move. But if you're at a reasonable size movie theater, there's not much for demand. Like the projectors don't take much energy. The sound system doesn't take much energy. They do popcorn and stuff like that, but they're not cooking burgers, or at least maybe they cook burgers now. I don't know, but I don't think most movie theaters do. So most movie theaters probably only use single phase. Not a lot of lower. Aaron, do you have another question? Or?
The lighting was incandescent, was it a lot more common? It was a lot more.
No.
Like an old movie theater that would have like crazy lights all over the place.
Well, old movie theaters would have a lot of light bulbs on the marquee, but even then, I mean, you're probably talking 25 to 50 watt bulbs because it seemed really bright, but it was always at night, right?
Yeah.
So even having a light bulb on, so if you had 100 bulbs, it's only 2.5 watts of kilowatts.
Yeah, which is still not that much.
It's not that much. So older ones probably would not. But this is where you got to be careful. Anybody want to buy a fancy dancy woodworking, like a wood lathe or anything like that? I can find them on eBay all day long, really, really cheap. But you better be careful. When you buy them, they're commercial and they're rated for 3-phase power, not single phase. So you're really happy. You've got this super duper lathe that can do all these fancy things. And you go to plug it in and it needs 3 wires and you've only got 2. It doesn't work. So you have to change the motor out, or you have to put a phase converter on it, which is very expensive. So be mindful that most of the time, if you're doing woodworking, you need to be very careful. And it's only because the motors, once they get big enough, you have to get 3-phase motors. They're just not practical to get them cheap. Yes, sir.
How can you do a phase converter except they
Super easy. Go buy a variable frequency drive. It takes,
they break it down and reconstruct it?
they convert it to DC and then they flip it out to AC for 3-phase. We have a senior project group this year that is doing exactly that.
Oh, yeah.
You're gonna plug it into the wall at 120 and output, you get 3-phase for, I don't know what their voltage is, but easy peasy. Well, I get a lot of power moving through it. So, yeah. Yep. So, but not that, probably under $1,000, maybe $2,000. Just again, depends on the size that you need. Excuse me. Here's the representation on a single line diagram. So we see all the connections here. We only see one phase here, simplifies it. And we see the transformers. Now it's a 300 kVA because we have three 100 kVAs. We have the loads. We show an impedance, which this will make a lot more sense when we look at it future on, but it says 5%, which is another way of saying the impedance. And then we have the voltages, line voltages. Yes, sir.
You said 100 kVA, is that like 100 kVA transformers? Or
Yep.
is that contained within one?
It depends. So if you're a utility, you buy 100 kVA pad mounted transformer or pole mounted transformers, and you can swap up them in and out. But if you're here on campus, most likely it's going to be all in one container because they don't have the resources to do it. Except when you go to some of these old buildings, like right across my office, and I mentioned this before, I think in this class, there's a caution do not enter door. It's a metal blast door. You walk in there, they have three pad mounted transformers, live exposed 4160 on the input, and then the output is probably 208. And they do that because it's just easier to go ahead and move into the building these three single phase transformers. And if there's a problem with them, it's easy to switch out. But you need special people to be able to work on those. It's exposed, so you have to have a fenced in area. It just takes more real estate and can cause more problems. But some of these old buildings, they actually have three single phase transformers. I don't think I wanted to take a picture inside there. Maybe I should reach out to the electrical shop and see if I can, because it's right outside my office. I mean, it's 10 feet from where I sit typically. All right, I'm really struggling here. Thought I was feeling better. And here's some of the load. It shows you 25 kVA per phase and 8 kVA per phase. And this would be the single phase representation if you just want to look at it a little bit differently. Here are some other connections. Here's a Y delta connection. So now I take the primary winding here, and then I just connect them into Y. And then my deltas over here. You will note that the phase relationship between primary and secondary is exactly the same. So the voltage in the primary is in phase with the voltage on the secondary. The current in the primary is in phase with the current in the secondary. So it's very, very important. If you notice, I have my A and B going across NP1 and NP2. I have my A and B here trying to go across one of these windings that matches it. But I think it was this class that talked about the phase shift between the bottom of campus and the top of campus. This is the problem. Why? Because over here, my A and B voltage, let's say it's at an angle of 0. But my A and B voltage over here is across this one winding. So this angle here, you can see, is different than the angle over here because there's going to be two transformers that would be there. So if you have a Y delta transformer or delta Y, you have to have a phase shift between primary and secondary when you're looking at line voltages. When you're looking at individual phase voltage, they're exactly the same. Yes, sir.
If you're Bergson, you could,
You don't?
Yeah.
You can always put an opposite transformer. You can put a delta Y transformer to give you the 30 degrees back. But most time it's not a problem because you're not connecting two different sources at different phase shifts. So like at your house, they'll run a transformer. Let's say your house is 3 phase. Why do I care? There's no source of power that I'm going to be backfeeding. So I don't worry about it. I just connect you at whatever value. It's only when I interconnect two systems, then I got to pay attention. And for the most part, you try not to interconnect too many systems, so you don't worry about it. But here on campus, there's not much they can do. So they don't worry about it usually. Although, like I said, somebody in this class said they may, I think it was actually the other class said they might have fixed it. I'm not sure. if that's the case, but no, it was the other class, right? That was that time when I showed you that image, that picture. You said it was a
Yeah.
69 kV line, and I think it was 325 class, so. But here's how you wire it up. Neutral, and then the delta. Look what I have to do. I have to go through each winding. And if you remember from lab yesterday, I said tip to tail fashion, plus minus, plus minus, plus minus. Aren't I connecting these in a tip to tail fashion? The minus is connected to the plus in all cases. And then I just come out on the individual lines where I have a common connection. That's a delta. And you can connect any set of three transformers in delta Y, Y delta, delta delta, Y Y, et cetera, et cetera. If you have to figure out the voltage ratios, always the turns ratio is going to be the phase voltage for primary and secondary side. If I do line voltages, then I take a look. My line voltage on my Y side is going to square root of 3 term because I'm looking across two phases. My delta, the line and the phase are the same. So I end up with a square root of 3 term there. So if I'm just looking at it, trying to calculate what my turns ratio is, I have to divide my primary voltage by my line secondary voltage. I have to divide that by square root of 3. Okay. So that does throw in an extra square root of 3 term. I also have a phase shift from a Y or a delta because when I look at my my neutral voltage here, it's 30 degrees behind when I compare that value here. But the individual voltage, the phase A voltage is going to match, but you can see this is V A to B. And so that's how I introduce the 30-degree phase shift. If you don't see it, you can do this. This is VA, VB. This is VA, or VB negative VB. So this is VA minus VB, vectorially added. This is theta, which is equal to 30 degrees. And since I'm looking across two lines or two phases of the transformer, I have to subtract those two voltages. Where in the delta, I don't. I only look across one. So when I compare line voltages on the output, I've got that 30-degree phase shift. Nothing I can do. So can I put a YY transformer in parallel with a Y delta transformer? No, I cannot, because I've got a 30-degree phase shift between those two. But can I put two Y delta transformers in parallel? Yes, as long as I make sure phase A connects to A, B connects to B, and C connects to C, then I'm in pretty good shape. So if you have to put transformers in parallel, which sometimes you do because the load is so great, you have to make sure that they're configured correctly, not just the voltages, but also the turns ratios of the transformer, the winding configurations of the transformers. Here's a delta Y, and now the delta is on the high side. No problem, it works there. But then our transformer, if you notice, now we have to multiply by the square root of 3. Okay, so our turns ratio has an additional 3, but then we have a 30-degree phase shift with the secondary voltage lagging the primary voltage. There are ways that you can change it to get almost any 30-degree phase shift you want, but we won't worry too much about that because that might cause some confusion in the class. Here's a delta delta. And again, I'm just trying to maintain phase relationships. Turns ratio is exactly the same. No square root of 3 there. Here is an open delta. What's an open delta? I'll pick on Noah because he's got all this power systems experience. What's an open delta? You don't see them that often anymore. Remember about utilities? I want to save money, right? So what if I tell you, I got a deal for you. I'll sell you 3-phase power. I'll sell it to you cheap. And you say, okay, deal. And then, unbeknownst to you, here's your connection. Any problem with that? Do you get 3-phase power over there? I get two-phase. What does the load see? Well, this is one at an angle of 0. Let's just pick one at an angle of 0. We have a balanced system. That's one at an angle of 120. What must the voltage be for KVL to be satisfied? We're going around a closed loop. Yeah. Doesn't it have to be there? So even if you but there's a problem because when you use two legs of a transformer, you think you get 2/3 of the power, correct? In a broken delta, an open delta. We'll talk about broken delta in a second. So let's look at some math here. So our power is going to be equal to VI cosine 30 minus 60, VI cosine minus 30. My VI cosine becomes cosine of 30 is square root of 3/2. Remember, we did that in class the other day. And then I do my other leg, and I have minus 150. Again, I have the square root of 3. So the open delta has 2 times the square root of 3/2, which is equal to the square root of 3 times V phase, I phase. When I do the calculation, I only have 58%. So I have two transformers, which should give me 2/3 of the power of a three-phase transformer, but this one only has 58%. So I think I'm getting something for nothing, but there's a penalty there. And the penalty is I'm only getting 57.7%. And look at the power for Q. I'm only getting half. So I have to do a serious derating to make it work. So you don't see open delta configurations anymore. They're not that common because buying an extra transformer is not that much more money. So open delta means we're missing one transformer. What's a broken delta? We have all three, but we open up one corner of the delta. That's a broken delta. Anybody want to guess as to why? Anybody here talk about zero sequence stuff in their jobs? What we'll be learning more next semester is you have zero sequence current that circulates in here. And if you open this delta and put a little resistor over here, you actually can monitor that zero sequence current. So it's a way of forcing a ground onto a system without having it there. So this is a broken delta, not an open delta. Not open deltas are way less common than broken deltas, and even broken deltas are not being that common anymore because of all the new relaying schemes. They make it so that you don't have to have this configuration like you used to have anymore. Oop. So that's the problem with open deltas. Don't see them much better anymore. You can do it. So if you want to be cheap and you don't need a lot of power, you can take your two transformers, run in an open delta, and you will get three-phase power. Questions? I know we're leaving a little early, but I'm struggling to not cough my brains out. I'm exceeding the recommendation of taking a cough drop every 2 hours. I must have taken 10 already today. I haven't been up for 20 hours, so. Any questions? Again, I apologize for missing lab yesterday afternoon, but I did the morning one, and I think anybody who was in the morning lab will tell you that it wasn't fun to hear me hack and cough the whole time. And I was just really struggling in the afternoon, so I just said I gotta do something different because I was worse in the afternoon. That wasn't planned. All right. Nothing else. Have a wonderful day. And I will see you all on Thursday. Take care. Take care, everyone.